Hello and welcome to week 2 of our virtual learning in higher chemistry. We are on the Nature's Chemistry unit of the course, and we are on topic 1 of this unit, which I'm calling an introduction to organic chemistry. I'm doing this unit in a very slightly different order to the way you might see in things like Scholar and BBC Bitesize. So just so you know, what we're looking at in this unit is in this topic rather is systematic carbon chemistry, oxidation and esters. Those are the kind of keywords you want to look out for in other areas. But I think it makes more sense to cover some of the core chemistry first. And then we're going to move on, like I say, to look at chemistry of cooking and cosmetic chemistry later on. So, like I say, this is week 2. Just as a little reminder, in week 1, that was mostly a recap of National 5, and in week 1, you looked at alkanes, alkenes and addition reactions, and alcohols. This week, we're going to look at the final part of National 5 revision, which is carboxylic acid, and then we are going to move on to look at the oxidation of carbon compounds. And we're going to look at definitions of oxidation and reduction for carbon compounds. Don't worry, the old definitions still apply, this is just a slight extension. And we're going to look at oxidation of alcohols, which also involves learning about substances known as aldehydes and ketones. So lots to do, very exciting week coming up. What I'm going to do is I'm going to talk through the notes and basically just let you know when I want you to stop and do some questions or maybe look at another video, because there are some practical experiments involved in this section which I would have loved to be able to do in class, but there are usually quite good videos of these online, so I'm going to just pause, get you to pause the video that I'm doing and go look at some other videos at various points. So let's get started. We're looking to complete page 17 to 26 of the notes this week. You don't have to do this all in one sitting. Remember, you can take breaks, and I'll try and direct you to points that you might wish to take breaks if I remember. So we're going to start on page 17, and page 17 is all about carboxylic acids. You don't have to look at these, but you can if you want to. I'm just going to direct your attention to the learning outcomes for carboxylic acids. So what you need to know about carboxylic acids is that you need to know that they're molecules containing the carboxyl functional group. So you need to be able to recognise that in a full structural formula and a shortened structural formula and be able to circle it. You need to be able to name and draw structures of straight and branched chain carboxylic acids, which contain up to 8 carbon atoms in the main chain, and you need to be able to name the products formed when carboxylic acids react with bases. So another thing you need to revise, this is National 5, but I suspect you might be a bit rusty, is recognising bases. So bases are metal oxides, metal hydroxides and metal carbonates. You need to be able to recognise these as things that will react with an acid. Okay, so the carboxylic acids. Well, you might remember a little bit about the carboxylic acids. One of the most common ones that we encounter in everyday life is ethanoic acid. So ethanoic acid is the acid found in vinegar. Remember from National 5, acids are often associated with quite a kind of sharp, tangy taste when you're thinking about food and drinks. So ethanoic acid is found in vinegar, and it's an example of a carboxylic acid. And we've got the what we call a ball and stick representation of the structure of ethanoic acid on the left here. Then in the middle we've got the full structural formula, and on the right hand side we've got the shortened structural formula. So you might remember the COOH group. So this group here, and it includes the carbon atom. This is known as the carboxyl group, and this is the functional group as it gives the molecule the chemical properties of a carboxylic acid. So the carboxylic acids with a structure based on an alkane structure form a homologous series called the alkanoic acids. What I mean by that is we get various different molecules in chemistry with this carboxyl group. Anything with the carboxyl group might be called a carboxylic acid, but we can get very complex molecules with carboxylic acids. The simplest carboxylic acids, however, are based on an alkane structure, and they form, like I say, a homologous series called the alkanoic acids. The alkanoic acids have similar chemical properties, physical properties that show a steady trend, and a general formula of CnH2n plus 1 COOH. Just be careful with this one. N does not represent the total number of carbon atoms in this general formula, because we have a final carbon atom here, COOH, in the end of this general formula. Just a little bit more background about the carboxylic acids or alkanoic acids, as well as ethanoic acid being found in vinegar. Another common one that you might come across is a methanoic acid, meaning only has one carbon. That can also that's generally known as formic acid as well. So I'll just show you the structure of formic acid or methanoic acid with only one carbon. So that's this one here. So you can see we've still got the carboxyl group because we still have a C with a double bond to an oxygen and then an OH group here. Methanoic acid, this one that I've got in my hand, is the acid that's found, among other things, in nettles, causes nettle stings, and also many ants have formic acid, and I think that might be why ant bites are so sore. So I can't remember if we discussed this at National 5, but the bottom of this page just explains a little bit about why these compounds are actually acidic. So they're acidic because they ionize, producing hydrogen ions in water. So remember, solutions with a greater concentration of H plus ions, hydrogen ions compared to hydroxide ions, are acidic. So what happens with these molecules is that they ionize in water. We could also say they dissociate when they're in water, and this is very similar to the dissociation of water itself. So what can happen is that the hydrogen atom, or rather the bond breaks, and both of the electrons in this bond, instead of being split equally, both of them are transferred to the oxygen atom. So we end up with an oxygen atom with an extra electron, an O minus, and an H plus a hydrogen ion on its own. So this is a dissociation or an ionization. It's reversible, as you can see from the arrows here. And another thing to mention is that similarly to the ionization of water, only a relatively small portion of these molecules will be dissociated at any one time. So we would say that they partially dissociate. Having these ions present in the solution of carboxylic acids means that they would conduct electricity. So what you've got to do now is, looking at this example here, you now have to write equations for the ionization of ethanoic acid using full structural formulas and shortened structural formulas. Before you start on that, I want to just mention something which I don't think we've looked at so far. We've got this R present in these structures. I like to think of R as standing for the rest of the molecule, and we will see this a lot in this unit, because quite often we want to talk about a generic generic family of molecules with a particular functional group, but it doesn't really matter what the rest of the molecule is. It might be the rest of the molecule. If we've got an R, that tends to stand for any kind of hydrocarbon section, although occasionally the R can stand for just hydrogen on its own. So you might want to make a little note of this down. So this R can be, I like to think of it as the rest of the molecule, because that helps me to think of what R means. But it usually refers to a hydrocarbon section, but that could have any structure. Or it could be a hydrogen as well. In most cases it could be a hydrogen. For example, if this was a hydrogen here, then that would just be methanoic acid, which we saw a little bit earlier. So what I'd like you to do is pause the video now and attempt question 1, and I'll go through question 1 once you've had a go. Okay, so if you're watching this, I'm hoping that you've attempted question 1. So that said, write the equations for the ionization of ethanoic acid. So if you think about it, looking at this example here, remember I said R stands for the rest of the molecule. In ethanoic acid, well, we've got the structure just at the top here, but you should also remember by now eth means 2 carbon atoms. So in ethanoic acid, this R is just going to be another carbon. So the ionization of ethanoic acid would be, okay, so you can see it given to you here, the full structural formula version on top, and then I've had to write the shortened structural formula underneath. I haven't put state symbols in here, but like it says in this here, it would most likely occur in solution. Okay, moving on to page 18 now, which looks at the structure, names and formulas of the first 5 members of the alkanoic acid homologous series. So remember that alkanoic acids are just carboxylic acids, but they are based on alkane structures, meaning they follow a general formula. Carboxylic acids is the broader term to describe molecules with the carboxyl functional group, this one here. I don't think you need me to give you any help on this page here, other than just to remind you perhaps that when we write the molecular formula for a carboxylic acid, a little bit like the way we do with alcohols, sometimes instead of just adding up all of the different atoms, we can write the hydrocarbon part but then still keep the COOH part separately, and even in the molecular formula, just to highlight that that is a carboxylic acid. So for ethanoic acid, rather than writing, you could write C2O2H4 as the molecular formula, but to be honest, you'd rarely see that for a carboxylic acid. So actually, with methanoic acid and ethanoic acid, the molecular formula is just going to be written in the same way as the shortened structural formula, so CH3C OOH. Okay, so pause the video now, make sure you complete the rest of this table. It goes all the way up to propanoic. Then you'll have to remember the name, what the name would be for carbon 4 carbons and 5 carbons. Okay, I'm moving on to page 19 now, but you should have already completed page 18. On page 19, we're going to do some practice of drawing and naming alkanoic acids with branches on the main chain. Now, these follow similar rules to what we've previously learned. Something that you might need to remember from page 18 is that the carbon with the carboxyl group, that is part of the carboxyl group, is always number 1 in the chain. And that makes these ones, I would say, a little bit easier than some other examples to draw. So I'm just going to go through the first one when it comes to drawing, and then you'll do the second two, and then again I'm going to go through one of the examples when it comes to naming, and then I'll get you to do the other ones. If you're feeling confident, then by all means pause the video now and try these, and then you can always look at my examples just to check that you were going along the right lines. So I'll start with the first one, 4-methylpentanoic acid. Okay, so we're going to break this up into the different parts of the name. Anoic acid tells us it's a carboxylic acid, which means it's going to have this carboxyl functional group that I've drawn up here. I should really, if I'm drawing the full structural formula, I should really draw that out fully like that. But I think you would get away with it the way I'd done it. Okay, so that tells us it's got the carboxyl group at position number 1. Pentanoic acid, pent means how many carbons? Hopefully you're thinking 5, so that means that there's going to be 5 carbons in the main chain, and 4-methyl means that there is going to be a branch with how many carbons? Okay, hopefully you're saying 1 carbon, so the branch has 1 carbon and it's on carbon number 4. So let's start, I'm going to work from left to right this time, just to show you how we can draw the carboxyl group, because I've drawn it like this, and you could also draw the mirror image of it. So first of all, pentanoic acid, I'm going to draw 5 carbons in a chain. 1, 2, 3, 4, 5. And then, just for illustration, I'm going to bring back my ethanoic acid here. So we can also draw the carboxyl group over this side of the molecule, and then we'd have the double bond to the oxygen up here and the OH down here. Equally, you could put it the other way around as well, so you could have the double bond and the OH up the top there. So there are different orientations in which you can draw the carboxyl group, because it can be spun around. I'm just going to draw it like this. For some reason, convention seems to be that we tend to draw the oxygen with a double bond higher up on the page, but it really doesn't matter. Okay, so this is then going to be carbon number 1, and then I've got 1, 2, 3, 4. I'm going to have a branch, a methyl branch on carbon number 4. So there we go, and then I just need to add in all my hydrogens. I'm adding in the correct number of hydrogens so that each carbon has 4 bonds. So it might be easier sometimes to draw the bonds in first. This carbon that's joined to the carboxyl group, it definitely won't have a hydrogen because it's already got 1, 2, 3, 4 bonds. Okay. Okay, so that's that one there. What you can do now is pause the video and try and do 2-ethylbutanoic acid and 2,2-dimethylpropanoic acid. Okay, so there's the answers for those two, so that you can check yours. I've drawn them in two different ways because remember, it doesn't really matter. These molecules can be picked up, turned over, twisted around, so it doesn't really matter the orientation in which you draw these. You could have the carboxyl group at either side of the molecule. You could have the ethyl branch either above or below the main chain. You could even draw it the other way around so that the main chain was going vertically. It really wouldn't matter as long as your carbons, as long as you've got 1, 2, 3, 4 carbons in a chain from the carboxyl group and then a branch of 2. Notice actually with this one as well, we could equally call this the main chain, 1, 2, 3, 4, and this could be the ethyl branch. It would be named the same either way. And then here's your 2,2-dimethylpropanoic acid. Again, we've got different mirror image versions that could be drawn. Okay, so question 3, we now have A, B, and then C on the next page where we have to name the acid given the structure. Now these are drawn as a slightly strange mixture of shortened structural formula and full structural formula. You would never actually draw these like this yourself in the exam. It's just really for ease of typing that these are like this on the page. So I'm going to go through the first one. Again, if you're feeling confident, pause the video now and do them all yourself. I'm going to go through the first one and then I'll leave you to do B and C. So in this first one, we've got to name it. So fairly easy because the carboxyl group, I might circle the carboxyl group in here just to help me. The carboxyl group is always going to be number 1 of the main chain, but we still have to find the longest chain. So 1, 2, 3, 4 if we go around this way, or 1, 2, 1, 2, 3, 4 if we go around this way. So either way, this has 4 carbons in the main chain, so this is going to be based on butanoic acid. And then there is, you can number them again if you want, 1, 2, 3. Whether we call this 4 or this 4, either way, there's going to be a methyl branch on carbon number 3. Remember methyl being a branch with 1 carbon, so this one's going to be 3-methyl butanoic acid. Now, when you're writing out the name for this, be careful, there's no space. It's 3-methylbutanoic, all one word with no space. Then there is a space between butanoic and acid. Okay, so just watch that. Okay, what I'd like you to do now is pause the video and do B and C. And when you come back to the video, I will pop the answers up so that you can check that you've done those right. Okay, so what I've got for B, I hope this is right, is I've said it's 2-methylpentanoic acid. Careful with this one, you've got 1, 2, 3 carbons here, but then you've got 1, 2, 3, but it tells you actually, remember I said it's a mix-up between the full and shortened structural formulas. It says this is C3H7, so that's implying that 1, 2, and then another 3 carbons continue in this chain here. So what we're actually going to assume is that this is the longest chain, but this one actually has another 2 carbons to make it C3H7, and then the methyl branch will be on number 2. So 2-methylpentanoic acid for B there. And then C, you've got a 5,6-dimethyl octanoic acid. Another, this one hopefully was quite obvious. The main chain goes across here, and we've got 8 carbons in the main chain. That's definitely the longest. And we've got these methyl branches on 5 and 6. And then this is written in a very similar way to what we did for alkanes and alkenes. So the numbers of the different branches are separated by a comma. Numbers are separated from letters by a dash. So this is 5,6 dash dimethyl because there are 2 methyl branches, octanoic acid because there are 8 carbons in the main chain. Something to watch out for is this COOH. When you see Q with a H in the shortened structural formula of a it's not a hydrocarbon of a molecule, then that's indicating to you that this is a carboxylic acid. So that's one to watch out for. As opposed to the, if you see COH, then that's well, it would actually be, if you say CH2OH, something like that, the OH on its own is telling you that that's an alcohol. Or if you see the OH in brackets as well, then that's an alcohol. Okay, I'm digressing a little bit. Right, we're going to move on to question 4 and 5. Question 4 says name the strongest intermolecular force between carboxylic acid molecules. And question 5 says state why the boiling point increases from ethanoic acid to pentanoic acid. And what I'd like you to do, just for a little bit of practice, is I'd like you to try and find the boiling point of ethanoic acid in the data book. I'm afraid pentanoic acid isn't actually in there, but you should see that the trend is that the boiling point is increasing as the number of carbon atoms increase. So pause the video now, answer these 2 questions, also find the boiling point of ethanoic acid in the data book, and then I'm going to just show you the answers in a wee second. So pause the video now and have a go. Okay, so you should have recognised that because alcohols have that OH, oxygen bonded to a hydrogen, that hydrogen bonds could form between alcohol molecules. So remember, hydrogen bond would form between the oxygen on one molecule and the hydrogen on another, that attraction there, or between the hydrogen on one molecule and the oxygen on another, that attraction there for hydrogen bonding. And then why the boiling point increases from ethanoic acid to pentanoic acid. If you look this up in the data book, ethanoic acid is 118 degrees C. It's going to increase. We don't have pentanoic acid in the data book, but you can see there that the trend is that the boiling point is increasing as the number of carbon atoms increase. So all I've said is that the thing to think about with this is that both substances contain London dispersion forces and hydrogen bonding, but in terms of the number of hydrogen bonds that the molecule can form doesn't change going from one to the other, because they both just have the same number of hydroxyl groups, of carboxyl groups. So the thing to bear in mind is that the more carbon atoms in the molecules, the more electrons in the molecule, and the stronger the London dispersion forces. You need to say something about stronger, and that's why pentanoic acid has a higher boiling point. And key thing is, when you're talking about London dispersion forces, to get this explanation in that the more electrons, the stronger the London dispersion forces. Okay, now would probably be quite a good point to have a little break in your work, and then we'll come back to look at the neutralisation of carboxylic acids in a little minute.